Hello everyone. So we ended up with this topic, no? So which is about measures of variability, no? All right. So we now proceed with our next topic. So sampling distribution of the mean and the central limit theorem, no? All right. So this is sampling distribution of the mean. So before I have already introduced to you the x bar, no? And x bar is the mean. Now mean here is a statistic, no? It is a characteristic of the sample, no? Now the mean has a sampling distribution, no? So when I talk about sampling distribution, it is the probability distribution of a statistic, okay? So suppose that a random sample of n observations, no, is taken from a normal population with mean mu. Alright, so this is the parameter. Okay, this is the parameter. I have introduced this before, no, concerning the population. No, so a random sample of n observations. No, so we take n observations. No, and then take it from a normal population. No, meaning the population is normally distributed. No? So I have already introduced to you normal distribution in the past. Okay, so the population is normally distributed, wherein the mean of that population is denoted by the Greek letter mu. So this is the Greek letter mu, okay, which is a parameter. And then the variance sigma squared, no? So this is the population variance, which is also a parameter. Okay, so we have two parameters to consider. Okay, so mu and variance sigma squared. Okay, so I have already introduced variance in the past, which is a measure of variability or a measure of dispersion. No? So each observation, x of I, for I equals 1, 2, and so forth, of the random sample will then have the same normal distribution as the population being sampled. Okay, because the observations were taken from a normal population, no? Now, if we take those observations, no? So, considering those observations that we take from that normal population, no? Now, as stated here, each observation, okay, of the random sample. So our random sample is x sub 1, x sub 2, up to x sub n. Okay? So our random sample will then have the same normal distribution, okay, as the population being sampled. Okay? So considering the random sample, it will also have normal distribution, no? Because we take these observations from a population which is normally distributed. So we now proceed. So this is the graph of a normal distribution. No? Now, as you notice, before this is only x, now is x bar that has something to do with the mean. No? It has something to do with the sampling distribution of the mean. Okay? So the sampling distribution of the mean is a normal distribution. Now we have here this is the notation u sub x bar. Okay, and this is the notation sigma x bar. Now, so before for a normal distribution, I have introduced to you mu and sigma. No, mu and sigma when I introduced the normal distribution topic. No, so wherein this is on the x. Since it is now x bar, we will put x bar as a subscript of mu, and also sigma, which is the standard deviation, as a subscript also. Okay, so in here, so this is the mean, sorry, the mean of the sampling distribution of x bar. So this is the mean of the sampling distribution of x bar. And then we have sigma x bar is also is the standard deviation of the sampling distribution of x bar. Okay, so note the following. So note the following. So mu sub x bar is equals to mu. No, sigma x bar equals to sigma over square root of n. Okay, so take note, this mu is the mean of the normal population, right? Mu sub x bar is the mean of the sampling distribution of x bar. Okay, so then sigma x bar is equal to sigma over square root of n. Sigma is the standard deviation of the population, okay, which is normally distributed. Then we divide it by square root of n, which is the number of observations taken from a normal population. No, dividing that, no, we get sigma sub x bar. No, okay. So we now proceed. So let me introduce to you the central limit theorem. So let's recall that to convert a normal random variable x of the normal distribution to standard normal random variable z of the standard normal distribution, so this is the formula. So z is equals to x minus mu over sigma. Considering the sampling distribution of the mean, okay, of the sample mean in particular, with mean mu sub x bar, okay, and standard deviation of sigma x bar. No? So z now is equals to x bar minus mu sub x bar over sigma sub x bar. No? So in this case, as you notice, the random variable x becomes statistic x bar. Okay, mu becomes mu sub x bar because we consider the sampling distribution of x bar. Okay, so it will have a notation mu sub x bar. For sigma, sigma sub x bar. Okay, now since the two are equal, so the mean the mean of the sampling distribution of x bar is the same as the mean of the population, which is normally distributed, no? And the standard deviation of the sampling distribution of x bar, no, is equals to the standard deviation of the normal population, then dividing it by the square root of the total number of observations that we take from that normal population, no? So therefore, this is now the simplified form. X bar minus mu all over sigma over square root of n. Okay? X bar minus mu all over sigma over square root of n. Now, the central limit theorem states that if a sample size n is taken from a population now with the mean mu and variance sigma squared, the limiting form of the distribution of z now equal to x bar minus mu over all over sigma over square root of n is the standard normal distribution now as n approaches infinity. Okay, so that's the limiting form of the distribution of z as n approaches infinity. Okay, so this is the formula. Now z equals to x bar minus mu over sigma over square root of n. Okay, now if n is greater than or equal to 30, the normal approximation for x bar will generally be good if the population is not terribly skewed. Okay, so meaning of course we're not expecting that it has a perfect distribution. Excuse me. Okay, so we're not expecting that it will have a perfect distribution, no? Provided that it should not be terribly skewed. So when we talk about skewed, it may be like this, no? So it could be negatively skewed or positively skewed, no? So something like this, no? Skewed to the right, distribution. Skewed to the left, distribution. Okay, so something like that. So if the population is not terribly skewed, no, so considering the variable x, no, the random variable x. Okay, so if the population is not terribly skewed, no, the normal approximation for x bar will generally be good for n greater than or equal to 30. If n is less than 30, the normal approximation for x bar no, will only be good if the population is normal. Okay? If the population is normal, meaning it has a normal distribution, which is this one. Okay? So we can use the formula for n less than 30. Okay? We can use the formula for n less than 30. if the population is normally distributed. No? Okay, in short, we can use the formula z equals to x bar minus mu all over sigma over square root of n for n equal to 30 and above. Excuse me. For n equals to 30 and above. No? So that's the distribution. It's of the random variable z. Okay? Of the random variable z. Okay. So this is the central limit theorem. No? So the central limit theorem, it is stated that if a sample size n is taken from a population with mean mu and variance sigma squared, the limiting form of the distribution of z equal to x bar minus mu all over sigma over square root of n is the standard normal distribution excuse me, as n approaches infinity. Okay. So we now proceed. So here's the problem. No? We have an electrical firm manufactures light bulbs that have a length of life that is approximately normally distributed, with mean equal to 800 hours and a standard deviation of 40 hours. Find the probability that a random sample of 16 bulbs will have an average life of less than 775 hours. So let us analyze. So we have a mean of 800 hours, okay? And we have also a standard deviation of the population, which is 40 hours. So we're required to find the average life of the 16 bulbs, less than 775 hours, no? So find the probability that a random sample of 16 bulbs, okay, will have an average life of less than 775 hours. So in this electrical firm that manufacture light bulbs, we selected 16 bulbs, no, from the population of light bulbs in that electric firm. Okay, then uh, the length of life of each bulb is measured, no? So what is now the average life? What is now the probability that the average life of 16 bulbs is less than 775 hours if the mean of that population of light bulbs in that electric firm is 800 hours, no? And the standard deviation of the light bulbs in that electric firm is 40 hours. So we proceed. So we let x bar be the statistic for the average life of the 16 bulbs, no? So this is the graph. Okay, so this is less than 775 hours, and we know that in this graph, this 800 hours is also equal to mu sub x bar, right? And it is obvious that this is 775 hours. No? This is x bar actually. No? The computed x bar. This is our random variable x bar, uppercase x. This is the value of the random variable x bar, or should I say the value of the statistic x bar, which is lowercase x bar, okay, which is equals to 775 hours. No? This is 775 hours, which is less than 800 hours. No? That's why this is the area shaded. No? because it's less than 800 hours. No? Okay. So what is now the probability that the statistic x bar is less than 775 hours? No? So recall, so this is the formula. So we just substitute the values. So the the mean, the computed mean is 775 hours. Okay, which is uh, the requirement of the problem, less than 775 hours. So that means x bar is equal to 775 hours minus 800. So this is the given mean of the population of light bulbs in that electric firm, all over 40, which is the standard deviation of the light bulbs in that electric firm, dividing it by square root of 16, where 16 is the total number of light bulbs taken from the population of light bulbs in that electric firm. No? And our answer is negative 2.5. So x bar will now be replaced by z, the random variable z. 775 hours will now be replaced by negative 2.5. So using table 8.3, okay, so our answer is 0.0062 using table 8.3. Okay, so let's see whether it's right or not. 8.3, 8.3. Okay, so let's see. So it is negative 2.5. So negative 2.5, that's about 0.0062. Okay, that's it, no? 0.0062. Okay, so that's our answer, 0.0062, no? So therefore, the average life of 16 bulbs less than 775 hours is equals to 0.0062. Okay? Alright, so we now proceed, no? Okay, number two. So we have traveling between two campuses of a university in a city via shuttle bus takes on average 28 minutes with a standard deviation of 5 minutes. In a given week, a bus transported passengers 40 times. What is the probability that the average transport time was more than 30 minutes? Assume the mean time is measured to the nearest minute. Okay, let's answer. So given okay, the mean is equals to 28 minutes, no? So the traveling between two campuses of a university, okay, in a city via shuttle bus. So that's the population mean of 28 minutes, no? So we have population of the time, no? The time of travel, okay, between two campuses. So that is our population time of travel between two campuses of a university. And considering that population of time of travel, the average is 28 minutes. That's why mu is equal to 28 minutes. And the average and the standard deviation of that population of time of travel is 5 minutes, no? So the standard deviation, sigma, is 5 minutes. So in a given week, a bus transported passengers 40 times. Okay, so we consider 40 times as our sample size. No, we consider 40 times as our sample size. Okay, so n now is 40. So what is the probability that the average transport time was more than 30 minutes? Okay, so we are to, excuse me, so we are to determine the probability that the average transport time was more than 30 minutes, no? So this is now the solution. So probability, so the average transport time denoted by x bar, the statistic x bar. So which is greater than or equal to 30.5 minutes. Because as you notice here, assume the mean time is measured to the nearest minute, no? So in other words, kung 30.5 yan, ibig sabihin nun, 31 minutes na yon. Kung 30.4 minutes, ibig sabihin nun, 30.4 minutes round down. So that's only 30 minutes pa rin. Okay? So it's still 30 minutes. Kaya kung 30.49 minutes, 30 minutes pa rin yan, hindi umabot ng 30.5. Okay? So ganun siya. Kasi may statement na assume the mean time is measured to the nearest minute. Kung wala yan, saktong 30 yan. Saktong 30 minutes. No? Pero dahil merong assume the mean time is measured to the nearest minute, ibig sabihin yan, 31 minutes pa lang, 31 minutes na may ko-consider kung 30.5 minutes yung time. Okay? So, kasi sabi dito, more than 30 minutes. Ang 30.5, masasabi na nating more than 30 minutes because it is measured to the nearest minute. No? So, because the mean time is measured to the nearest minute. Yun ang reason. No? So, more than 30 minutes na nun. Yung 30.5 minutes. Pero kung 30.49 minutes, that's not yet more than 30 minutes. Okay? So, that's it. I hope you get it. Now, mean time is measured to the nearest minute. So, this is the graph. As you notice, no? So, this is 28 minutes, no? This is 28 minutes, no? So, that's the mean of 28 minutes. And then we have 40 as our sample size. This is 30.5. This 30.5 minutes is here. So it is here, 30.5 minutes, no? Which is x bar. The value of the statistic x bar. Okay, 30.5 minutes. So it's greater than, no, the mean of 28 minutes, no? And the area shaded here denotes the probability that the average transport time, denoted by x bar, is greater than or equal to 30.5 minutes. Okay, so notice that. So this is greater than or equal to 30.5 minutes. No? So because of the reason that pag 30.5 minutes, that is already 31 minutes. Okay? So that is already more than 30 minutes. No? That's why we include equal, less, greater than or equal. No? So, pag 30.49 minutes, that is still 30 minutes. No? So, in that case, this is not yet more than 30 minutes, 30.49 minutes, if the mean time is measured to the nearest minute. I hope you get it. Okay. So, this is our concern now. The probability that the the mean is greater than or equal to 30 minutes, which is this shaded area to the right. So let us answer the problem. So recall that this formula, okay, the central limit theorem, we recall the central limit theorem. No? Applying the central limit theorem, so we have 30.5 minus 28 all over 5 over square root of 40. And then our answer now is 3.16. All right, so in this case, we use table 8.3, no? We use table 8.3 to determine our answer. So as you notice, this is area to the right, no? And that is 1 minus probability, my 1 minus area to the left, okay? So that is 1 minus probability z less than or equal to 3.16, no? Okay, so this is obtained in the table 8.3, no? And our answer is 0.0008, no? Okay, so we then conclude, no? We then conclude that the average time, no? The probability that the average transport time is greater than or equal to 30.5 minutes is equal to 0.0008. Okay, so that is very small, no, or very little chance, no. There's a very little chance that the average transport time will be greater than or equal to 30.5 minutes, no. So in short, there's a little chance that the average transport time will be more than 30 minutes, considering measuring time to the nearest minute. No? Okay, that's it. I hope you get it. No? So we now proceed with sampling distribution of the difference between two means. So if independent samples of size n1 and n2 are drawn at random from two populations, with means mu sub 1 and mu sub 2, and variances sigma 1 squared and sigma 2 squared respectively, then the sampling distribution of the difference of means is approximately normally distributed with mean mu sub x1 bar minus x2 bar and variance sigmas squared x sub 1 bar minus x2 bar. Okay, so in here we have difference between two means. Okay, so let's analyze. So we have samples of size n1 and n2 are drawn at random from two populations. So we consider two populations. Let's say population 1 and population 2. From population 1, we take N1 as samples. For population 2, we take N2 as samples. Now, this population 1 has a mean mu sub 1. Population 2, a mean mu sub 2. Population 1, it has a variance of sigma 1 squared. Population 2, it has a variance of sigma 2 squared. And then, considering that population 1, which we take N1 as samples, we can compute then the mean, okay, x1 bar. Okay. Then for population 2, when we take n sub 2 as samples, we will have a mean x2 bar. Okay. Now, if we take the difference between the means, no, x1 bar minus x2 bar, since population 1 is normally distributed and also population 2 is normally distributed, it follows that x1 bar minus x2 bar will also have a normal distribution, okay, which is approximately normally distributed. Okay, so the mean now is mu sub x1 bar minus x2 bar. So you have the graph approximately normally distributed and the variance sigma squared x sub 1 bar minus x sub 2 bar. So in here we have the standard deviation sigma sub x1 bar minus x2 bar. Okay, so we now proceed. So we have, so take note that mu sub x1 bar minus x2 bar is simply the difference between two population means. The difference between the two parameters, parameter mu sub 1 and parameter mu sub 2. Okay? And then the standard deviation of the sampling distribution of x sub 1 bar minus x sub 2 bar uh, is equals to the square root of the variance of population 1 over the number of observations taken from population 1 plus the variance of population 2 over the total number of observations taken from population 2. Now, when we do that, we obtain the standard deviation of the sampling distribution of the difference between two means. No? So recall, okay, to convert a normal random variable x, excuse me, so to convert, excuse me, to convert a normal random variable x of the normal distribution to standard normal random variable z of the standard normal distribution. So this is the formula. So considering the the sampling distribution of x1 bar minus x2 bar with mean of mu sub x1 bar minus x2 bar and standard deviation of sigma x1 bar minus x2 bar. So this is the formula. No? Okay. So x becomes x1 bar minus x2 bar. Mu becomes mu sub x1 bar minus x2 bar. Sigma becomes sigma sub x1 bar minus x2 bar. Okay, so, and you know this, I have introduced this already. Okay, so therefore, this is our formula. Okay, this is our formula. So this is x1 bar minus x2 bar. Then mu here will be replaced by mu1 minus mu2. Okay, then sigma here will be replaced by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so that's the formula. So let's apply the formula. So later for our example, we will apply it. So if n1 is greater than or equal to 30 and n sub 2 is greater than or equal to 30, the normal approximation for the distribution of x1 bar minus x2 bar is very good. Excuse me. When the underlying distributions are not too far away from normal. No? Letter B, if n1 is less than 30 and n sub 2 is less than 30, the normal approximation for the distribution of x1 bar minus x2 bar is reasonably good, no? Is reasonably good, except when the populations are decidedly non-normal. Okay, letter C, if both populations are normal, then x1 bar minus x2 bar has a normal distribution, no? Regardless of the sample sizes n1 and n2. So take note of the following, no? Okay, so in short, we can able to use the formula, no? We can able to use the formula that I have introduced in the previous slide. If the number of observations for each population, the number of observations that we take from each population are greater than 30, no? Okay, so if they are less than 30, we can still use the formula, okay, provided that the two populations should be normally distributed, no? We can use still we can use the formula still, no? If the two populations are normally distributed, no? So the normal approximation for the distribution is reasonably good except when the populations are decidedly non-normal. Okay? So then letter C, if both populations are normal, okay, then x1 bar minus x2 bar has a normal distribution now, regardless of the sample sizes n1 and n2. Okay, so in short, if population 1 and population 2 are normally distributed, x1 bar minus x sub 1 bar minus x sub 2 bar has also a normal distribution, no? Regardless of the sample sizes n sub 1 and n sub 2. So I hope you get it. Okay, so let's answer a problem. So we have two independent experiments R1 in which two different types of paint are compared. 18 specimens are painted using type A, and the drying time in hours is recorded for each. The same is done with type B. The population standard deviations are both known to be 1.0, assuming the mean drying time is equal for the two types of paint. So find the probability that x bar sub A minus x bar sub B is greater than 1.0, where x bar sub A and x bar sub B are average drying times for samples of size n sub A equals to n sub B equals to 18. So let's analyze. So given we have type A and type B paint, no? Okay, so for type A paint, we have the standard deviation of 1.0, no? So this is the standard deviation. So the population standard deviations, that is sigma. no, are both known to be 1. Same as type B, no? Okay, then assuming that the mean drying time is equal for the two types of paint. That's why mu sub A equals to mu sub B, considering the population, no, of the mean drying times. Okay, and then required in the problem is to determine the probability that the difference between the two means will be greater than 1.0. No, wherein we selected 18 specimens, no, for type A, 18 specimens for type B. Selecting 18 for type A and 18 for type B, what is now the probability that the difference between two means will be greater than 1? No? Solution to the problem. So we assume that XA bar minus XB bar is normally distributed. So this is the formula. No? Okay, so we use subscript A and subscript B. So x1 becomes xa, x2 bar becomes x sub b bar. Okay, that's it. N sub 1 becomes n sub a, sigma 1 squared becomes sigma a squared, and so forth. So this is we substitute the values now. So the difference xa bar minus xb bar is 1. Okay, because we're looking for the probability that x a bar minus xb bar is greater than 1, right? Let's see. Here, greater than 1. Okay? Okay, so that's why this is 1. And then, this is 0 because mu sub A equals to mu sub B. They have the same drying times. No? Mu sub A equals to mu sub B. That's why this is 0. Then the standard deviation is 1 for each paint. No? 1.0, 1.0. Then 18 for specimen for 18. Okay, using type A paint. So we take 18 using type A paint. We also take 18 using type B paint. No? So that's it. So we get 3.0 as the value of Z. No? And then we this is now Z greater than 3.0, and this is area to the right of table 8.3. So this is we should obtain area to the left, no? So that we can use table 8.3. So what is 1 minus this probability? So 1 minus 0.9987. Using table 8.3, we get this value when our answer is this. So the 0.0013. Okay? So the probability that the difference between two means will be greater than 1.0 is equals to 0.0013. So that is very little chance now. Okay, that's it. I hope you get it now. So number 2, the television picture tubes of manufacturer A have a lifetime of 6.5 years and a standard deviation of 0.9 year. while those of manufacturer B have a mean lifetime of 6 years and standard deviation of zero point 0.8 year. What is the probability that a random sample of 36 tubes from manufacturer A will have a mean lifetime that is at least 1 year more than the mean lifetime of a sample of 49 tubes from manufacturer B? So we have for manufacturer A 6.5 years mean, standard deviation of zero point 0.9 year, okay? And then for manufacturer B, okay, so this is manufacturer A, have a mean lifetime of 6.5, standard deviation of zero point 0.9. For manufacturer B, mean lifetime of 6 years, and standard deviation of zero point 0.8 year. Now, so what is the probability that a random sample of 36 tubes from manufacturer A will have a mean lifetime? So as you notice, so the sample size is 36 for manufacturer A. Now 36 for manufacturer B, 49. So 49 tubes for from manufacturer B. Okay, so required. So this is the probability, no? So probability that x sub a bar, no? The sample mean for manufacturer A is greater than or equal to the sample mean for manufacturer B plus 1.0 year, no? Kasi sabi dito, what is the probability that a random sample of 36 tubes from manufacturer A, no, will have a mean lifetime? So this is the mean lifetime for manufacturer A, no? Will have a mean lifetime that is at least 1 year more. Kaya meron plus 1 year. That is at least 1 year more than the mean lifetime of a sample of 49 tubes from manufacturer B. Kaya naka-add yung dalawa, no? XB bar plus 1. Plus 1 year. Greater than or equal to. So, dito, no? X sub A bar greater than or equal to X sub B bar plus 1.0 year. Okay? Okay, so we now proceed. So note, no? This probability is also the same as this one. So transpose natin to the left, x sub a bar minus x sub b bar greater than or equal to 1 year. No? So we now proceed. No? So assuming x sub a bar minus x sub b bar is normally distributed. No? So this is the graph. So this is 1 year. And this is our concern. Find this probability. Okay, so this is the formula. Okay, so and then we just substitute, no, the values. We get 2.65, no, and our answer. So this is greater than or equal to 2.65. Here, this is area to the right. So let's convert it in terms of area to the left. So we can now use the table 8.3 to determine this, no? So our answer is 0.004. So that is our answer, no? Okay, so that ends my presentation. So I hope you get it. Good day, everyone.